Our next speaker in the session is Longfei from Fudan University. He's a faculty member at Fudan University in Shanghai, China. He is the director of FPGA and High Performance Computing Lab at Fudan. Mr. Chang got his PhD degree from UCLA in 1999 and has been working in the EDA area for 30 years. His research interests are RTL synthesis and high-level synthesis for high-performance computing, performance-driven partitioning, and layout-driven synthesis, and high-performance neural network computing design.
Okay. Thanks for the introduction. Can you hear me? Okay. Yeah. My name is Chen. I'm glad to be here to present our work on FPGA technology mapping with adaptive gate decomposition. My student Longfei couldn't come here, so still. Hello? Yeah, my student Longfei couldn't come here due to this visa and coronavirus issue here. Yeah, FPGA technology mapping is a well-studied problem, and most existing approaches use the covering-based mapping, which requires the nets to be decomposed into k-bounded netlist first. However, the gate decomposition can play a big role in this mapping result. Let's look at a simple example. This is widely used in data bus design, basically the 8-bit equality comparator. If we do this default decomposition, we will get a result of 4 6 slots with 3-level logic. However, if we do a different decomposition, then we can get a 3-lot with 2-level logic. The natural question is how we find the best decomposition for mapping. So there are some existing mapping with decomposition approaches based on the so-called choice node. A choice node is a node with all the input are equivalent, logically equivalent, which represent different decompositions of this wide gate. For example, here is an example of a choice node with 2 inputs representing 2 different decompositions of a 3-input gate. So the choice-based approach will first pre-generate a set of decomposition choices for wide gates, and then map all the choices and choose one with the best QR. The problem with this approach is that the decomposition choices for wide simple gate can go exponential, and it's very difficult to know a good set of choices before mapping. And later on, Sajid and Allen's group proposed the lossless synthesis-based choice generation, basically to save the intermediate steps of the various generic logic organization and to form the choices. However, this approach, the problem remains the same. Basically, we don't know if the choice set generated are good enough or not. So here we propose a simultaneous mapping decomposition approach, so as to avoid the pre-generation problem. Our work is an extension of the previous priori algorithm based on the cut-enumeration, pruning, and the ranking approach. Our contribution here basically is a cut-enumeration for wide simple gates. And also we combine the beam packing based gate decomposition with the cut-enumeration and the ranking. And at the end, we also propose an iterative cut selection based on the input sharing for duplication reduction. Yes, here I'll give a brief review about the cut-enumeration approach, the priori algorithm. Basically, based on the observation that a node's k-cut is also its input k-cut. Thus, they can use a dynamic program to enumerate all possible k-cuts for a netlist. And then also propose an effective area based on the family distribution and use this effective area to do the cut ranking and the pruning. This approach enables efficient FPGA mapping for large K. Yeah, obviously we can see basically for the wide simple gate, we can use this approach to enumerate the cuts as well, except that here we'll get a wider cuts. And the effective area computation will be similar here, except that the cut itself, the area is no longer 1 because it's a wide cut. So we have to find out the area for the wide cut. And fortunately, we can use the beam packing approach. Beam packing is the first lot-based mapping algorithm which proposed by Jonathan's group in 1991. Yeah. And the beam packing approach basically view each input cut as a small beam and then use a size k beam to pack them together. And then the beam packing can formulate a mapping solution. So in this way, we can compute the wide cut area very effectively. So within beam packing, basically, we can extend the previous priori algorithm to do this cut-enumeration, the effective area computation, and the pruning, basically. And then after the bin packing for the wide cut, we can use the root K cut as a cut propagation for its fan out and continue to do this cut-enumeration for entire network. One problem with this approach is that the number of K cut for wide gain can go to the C to the power of W for gate with wide W inputs. This can be a very huge number. So we propose a heuristic to do the fast cut-enumeration for this wide gate. The capacity is reduced to WC square. So our algorithm idea is quite simple. Basically, we just try to enumerate the cuts for one input at a time instead of for this entire set of inputs. So basically, we first get a netlist which is empty at the beginning. So we use this cut netlist to do the cutting combined with another input cut list to get a new list and then continue these steps. So for this partial cut, when we do the ranking, we ignore this cut itself area. We basically just get the fan Cong's area. And for the full cut, then we will perform the bin packing to get the cut area as well. So in this way, basically, we can do the entire netlist. We can do the cut enumeration and the ranking and the pruning. So after that, we need to find the mapping solution based on the previously generated cuts. So this cut selection is quite straightforward. Basically, we do a post-processing basically to traverse nodes from PO to PI to find all the lat roots and the corresponding cut to form the mapping solution. So at the beginning, we mark the PO as root. The rest are not, right? Then for each lat root node, we will select the best cut and then continue to mark the input as cut root as well. So in this process, we can traverse the netlist and form a solution. However, here for this mapping duplication reduction, we propose a new formula to this cut evaluation by adding a fan sharing factor MI here. So for a given cut, if an input I is marked already as root, we will set MI to be 0. Basically, ignore this fan Cong's area. In this way, because we will share favor cut which shares input with another cut. So basically, based on this new cost computation, we will favor cuts which shares the input. And after one iteration, we can get a mapping solution. We can evaluate its total area and compare with the previous iteration. If there's an area reduction, we will continue the process until at the end no area reduction. Then we will stop to get a solution. So here is our experiment result to compare with the ABC lossless synthesis. And also we combine the loss synthesis with the set-based remapping to see how good they are. We choose a set of benchmark from EPFL and some computation-intensive design generated by HLs for and K set to be 6. So here the result is normalized to ABCLS. So from the result, we can see that we can quite consistently get the best result. We can get an average 12.4% reduction over ABCLS. Even for the ABCLS plus set remapping, we can still get a 4.7% error reduction. And also our algorithm can be extended for the delay optimizing as well. The only change is that for each cut, besides the area cost, we also compute a delay cost. And the ranking also a bit complicated. Basically, we'll consider delay first and the area second. So here we also compare for the delay-driven mapping, we compare same as ABCLS and ABCLS plus set remapping. Here on the delay side, all the 3 approaches compute the same delay, except there's one design, the log2 AGDMap, get a slightly better, 2% less delay. And for the error comparison, basically we can get a 9.2% error reduction over ABCLS and 7.4 error reduction over ABCLS plus satellite mapping. Yeah, as a conclusion, basically we perform this simultaneous cut-enumeration and gate decomposition. We can achieve 9 to 12% error reduction over state-of-art result for error-driven mapping or delay-driven mapping. So in the future, we will consider the complex gate decomposition in this mapping approach as well. Okay, that's the end of my talk. Thanks for listening.